Hey everybody, welcome to this video, which is going to be covering some of the exponent rules. And not only showing you these exponent rules that you've probably seen in textbooks and other things you've learned, but trying to break them down a little deeper and hopefully have you leave with an understanding of why the rules are these shortcuts or these things that you can use with exponents. So during this, we're going to start off with just really breaking it down into what is an exponent. And then we're going to look at some of the special rules that go with exponents, the ways we can multiply exponents, divide exponents, all kinds of different things in this video or others in the series. So I'm excited you're here, and let's get into it. In the comments below, I've included a companion Nearpod lesson, so you can practice some problems to make sure you're understanding the video and understanding the concepts. If you like this idea of including these with my videos, please definitely comment and let me know. And subscribe to the channel to see the other videos that I upgrade in the same way. Before we get into it, I want to use this guiding question for you. Make sure that as we go through each example, you don't just understand how I got the answer, but you understand the why. Why did it work that way? Why is this shortcut useful? And why is it possible? If something doesn't make sense, you need to make sure you rewatch it. First thing we're going to look at is exponential form. And you've probably seen an exponent before because they all kind of look like this, where you have a number with a smaller number raised up on the right side. Each of these numbers has a specific name. The larger blue number on the bottom is referred to as the base. This is the number that will be multiplied out however many times the exponent specifies. The exponent is that number that I have in yellow that's raised up. Sometimes you may have to write the exponent yourself and you'll see it in word form. There's a couple different ways that you're most likely going to see it. First is 5 raised to the 6th power. And the second is 5 to the 6th power. So they're just leaving out that raised verbiage. We're going to take a look now at how this looks when you write it out without the exponent. When you write it out, this is known as expanded form. They're called forms because it's the same number in two different ways of looking at it. It's kind of like a folding chair. The chair can be folded up and we know what it is, but when we expand it out to its full potential, we can look at it differently and use it differently. So let's take a look at a couple of examples of exponents in both exponent form and then expanded form. First, you have 5 to the 2nd power. As you can see, we have a 5 for our base and a 2 for our exponent. That means that that base of 5 is going to be multiplied by itself 2 times because the exponent dictates the number of times we multiply. From there, we can go ahead and simplify that to its numerical value of 25. Next, we have 6 to the 5th power. This means that we have a base of 6 and an exponent of 5. Before I show you what this is in expanded form, take a moment, pause the video, and try to write it out yourself. Expanded, that means we take the number 6 and we multiply it by itself 5 times. And as before, you can then simplify, but I need a calculator for that one. Next, we're going to look at a couple special cases. And really, special cases are things to watch out for because they're the only twists that you'll see with these exponents and what you got to watch out for and understand. The first is the dreaded fraction. It really doesn't change the way you write out a fraction in expanded form. What changes is paying special attention to the multiplication step. So in this example, when we have 1/3 to the 3rd power, as before, it means it's going to be 1/3 times 1/3 times 1/3, or 1/3 multiplied by itself 3 times. The trick here is to remember with fractions that you multiply straight across the top, or the numerator, and then straight across the bottom, the denominator, to get your simplified answer. This leaves you with 1 times 1 times 1 on top, which is 1, and 3 times 3 times 3 on the bottom, which is 27. The next special case is the negative exponent. Here you see 2 to the negative 3rd power. The base is 2 and the exponent is -3. The trick with a negative exponent is to remember any number can be written over 1. We simply take that negative exponent and the base and move it entirely to the bottom of the fraction or the denominator, leaving a 1 on top and a positive exponent now on the bottom. The same would be true if it was on the bottom of a fraction. You could move it to the top and change it to a positive exponent. To simplify, since the whole 1/2 is not inside parentheses, we simply take the bottom, and 2 times 2 times 2 is 8. The third special case is a number raised to the 0 power. In this case, 3 to the 0 power. What I want you to do now is I want you to think, what do you think 3 to the power of 0 will be? And even more, why? Pause the video and think about that for a second. When you hit play, you'll see the answer, and you can see if you're right. That is equal to 1. In fact, any exponent to the 0 power is equal to 1. This is a particularly tough one for students to remember. So let's take a look at something I used to teach my students to help them remember it. To do this, we're going to think about a piece of paper. Representing this activity with an exponent, the base of the exponent is how many equal-sized pieces we'll fold the paper into, 2 being folding it in half. The exponent is the number of times that we're folding it, in this case in half. Folding it 1 time, representing an exponent of 1, leaves you with 2 pieces of paper thick, or 2 equal sections. Let's continue this idea. If I folded that paper in half again, that could be represented by 2 to the 2nd power. And now I have my paper in 4 equal sections, or 4 pieces of paper thick. If we fold it in half a 3rd time, we could represent that with 2 to the 3rd, and 8 pieces of paper thick, and so on. So what is the purpose of this activity? Let's think about the piece of paper. How would we represent the piece of paper before we folded it? Well, we have folded it 0 times. But how thick is that piece of paper? Or how many equal sections have we had? As you can see, it's 1. It's kind of a clever way to remember that anything to the 0 power is 1. The number of times we folded it was 2, but we could have done this for the 3rd power, 4th power. It would do the same, it would just be folding it into 3 or 4 equal sections. Hopefully this helps you remember. So next we're going to look at some of the rules around arithmetic with exponents. We're going to start with something we call the general case. And that's because we have, in the exponent place you notice, letters. What we want to do is we want to be able to start with concrete real numbers, but figure out a rule that will work for all numbers, because that's how rules work. They work all the time. We're going to start off with multiplication. As you can see, we have m and n as the exponents with a base of a. What we're looking for is to come up with a rule that we can say with that m and that n, what is true every time you multiply 2 numbers with the same base? What happens with the m and the n? We're going to use a specific example with exponents 4 and 3. And what we're going to do is write them both in expanded form to kind of see if we can figure out the rule. So first, let's take a look at a to the 4th. That can be written as a times a times a times a, 4 of them basically. We're going to continue to have that white multiplication symbol that we're using for the problem. And we're going to also break down a to the 3rd into expanded form, which is 3a's. We'll take a look. If we were to simply remove the parentheses, we'd have 7a's all together multiplied by each other. Well, that can be written as an exponent as well. Pause the video and think, what would that exponent be? a to the 7th. Pause the video and try to think, how could we have gotten that number without having to write it out in expanded form? Is there a way to know ahead of time that it was going to be a to the 7th? So the rule then is that you simply add the exponents. And we can apply that to the general rule as well, where a to the m times a to the n is equal to the a to the m plus n. This will work for any values of m and n. So let's take a look at some practice problems where you'll pause the video and give them a try on your own. Definitely take the time to pause so you can check if your answers are correct. Notice that in all answers, all we really did was add the exponents. Pay special attention to the numerical base ones. A very common mistake for students to multiply those. So taking the middle one, for example, they might put 4 to the 7th power. But that doesn't make any sense. There isn't 7 4s, there's 7 2s, because really all you're doing is expanding out the numbers. Next, let's take a look at division. Again, with a general case of m and n, we want to find a rule. Let's start with some specific numbers. Let's try a to the 6th divided by a to the 2nd. Before we begin, do you have a guess what this will be? Take a second and think about that. What do you think a to the 6th divided by a to the 2nd will be? If you don't guess, you can't have a chance to be right. So pause and think about it for a quick second. First thing anyone's going to want to do is put a to the 3rd, 6 divided by 2. But we need to take a second and figure out how this actually works when we break it down. Remember that a division sign can also be a fraction bar. Given that, write this out in expanded form, with a to the 6th in the numerator or top position of the fraction, and a to the 2nd in the denominator or the bottom of the fraction. Let's just check that you're expanding it correctly before we look at the rule. If we expand our numbers, you're going to notice that we have 6 a's on the top of a fraction bar, which is replacing the division sign, and 2 a's on the bottom. Every time you have on the top and bottom the same number or variable, you can divide them out and leaving 1. What we often see is people crossing them out, as you see here. So now that we've simplified, what is left in this fraction? Take a moment to think about that. A lot of students make a very common mistake here, which is to think that there is nothing or 0 left on the bottom of the fraction. Remember, every time we crossed out an a from the top and the bottom, it was divided out to be 1. So if we do that, we still have a number on the bottom of the fraction. It's just a 1. And when the 1 is the only thing on the bottom of a fraction, there's no need to write it as a fraction anymore. Meaning all we have to do now is write what is left on the top of the fraction. Once you do that, what you're left with is 4 a's multiplied together, or a to the 4th. Now that we've figured out that a to the 6th divided by a to the 2nd is a to the 4th, can you find a shortcut or a rule for this type of problem? Pause the video and think about it. Notice that to get from a 6 divided by 2 to a 4, we're actually subtracting the exponents. Which kind of makes sense since multiplication is adding exponents. Applying that to the general rule, you'll notice that we now have a to the m divided by a to the n is a to the m minus n. Now let's take a look at some practice problems. As before, pause the video and give yourself time to try each problem. Then come back and check your answers. As before, each answer is simply subtracting the exponents. Be very careful not to divide the bases. Same as before, it's a very common mistake. For example, if we take a look at the first problem, some students would put 4 to the 6th divided by 4 to the 3rd is 1 to the 3rd. Try to remind yourself that all you're doing is eliminating some of the 4's. It's not going to magically turn into a bunch of 1's multiplied together. Plus, 1 to the 3rd is just 1 times 1 times 1. So that's just 1. We know the answer isn't going to be just 1. Let's take a look at what happens if you're dividing exponents and the one on the right is actually larger. What happens is, as you simplify and expand, then cross off top and bottom, everything on top will be eliminated.
This is another common mistake. Watch out for what happens when you divide 4 divided by 4.
Take a second to think about it. What is left on top of this fraction?
4 divided by 4 is 1, not 0. So there should be a 1 left over on top and 5 4s in the bottom. Our shortcut rule tells us that 2 subtract 7 is -5, but students often mess that up. Be very careful, and my general rule of thumb is to always write out division problems. Next, we're going to take a look at an exponent raised to another exponent. Again with a general rule, but let's start with something specific. In this case, a to the 4th to the 3rd power.
Let's take a quick pause here. Do you have any guesses as to what you think this rule might be? Think about it for a second. Think about what that exponent on the outside means. See if you can figure out the rule before we say it.
Let's take a look at what that means. It means you have a to the 4th multiplied by itself 3 times.
Did that help? Do you think you see the shortcut now? Let's see.
Using our shortcut, 4 plus 4 plus 4 equals 12. That means that really what you do is you actually end up multiplying the exponents.
Applying that to the general rule, that means when you have a number outside the parentheses, like n, you multiply m on the inside by that number. And that's our general rule.
Let's take a moment and apply that on some practice problems. I recommend you pause the video, complete the problems, and then hit play to go over the answers. As you can see, all we do is leave the base as is and multiply the exponent by the exponent outside the parentheses. Again, nothing changes the base. So this begs the question, now that we have rules for multiplication and division, what about addition and subtraction? Is there a rule, a shortcut, a little trick you can learn to be able to know something like this, a to the 2nd plus a to the 5th? So think about that. Could there be a rule? To kind of explore that, as I did before, I think the best thing to do is put in a real numbers example that you can calculate. So 2 to the 2nd plus 2 to the 3rd.
Let's take another pause and let's think of some possible rules that could go with addition. Make a list, either mentally or on paper. Just think of as many possibilities as you think might work out. Let's see if you can guess it.
Let's simplify that out. Well, 2 to the 2nd is 2 times 2, so that's 4. 2 to the 3rd is 2 times 2 times 2, that's 8. If you add those together, you get 12, right? Well, what might a shortcut be? It could be something like 2 to the 5th, right? Maybe you add them together. Well, 2 to the 5th, though, is 32, not 12. What else might be a possibility? Other people say maybe 2 to the 6th, right? Well, that's 64. Okay, that's 2 times 3. Yeah, that's not it. So the shortcut isn't to add the exponents or multiply the exponents. If you take the time to actually think about it, the way exponents work is it's repeated multiplication. Throwing a random addition sign in there just doesn't make sense. So in fact, there is no rule for those. The only rules we have are multiplication, division, or raised to an exponent, which is really just multiplication repeated. So if you have exponents with a variable base, like in this case a, they already are as simplified as possible with an addition sign. When you see a problem like that, it's actually testing, do you know that there isn't a rule about combining those two? Before you leave, I have one more thing I want you to do. We talk about how every single time the exponents have the same base for our multiplication, division, and exponent to the power rule. Do you think that that base could be different? Or why does it have to be the same base? Use the comments to add something to the conversation below.
Thanks everybody for watching. That's all we have for this video. I do encourage you to check out some of my other videos.
And this is really the first video I've created sort of since I've learned a lot of new video skills as an instructional designer at the college level. So if you have the time, please go ahead and comment on the video some of the other videos I have that you'd like to see upgraded to this newer version and newer format. And of course, if you want to subscribe, you want to like these videos, that obviously helps me out too to keep being able to make more of these videos. So thank you guys so much for watching. Hope to see you in the next one.